The next topic is solar cell. A solar cell is basically a PN junction which generates EMF when solar radiation falls on the PN junction. I'll repeat again. A solar cell is basically a PN junction which generates EMF when solar radiation falls on the PN junction. So this is the circuit symbol of the solar cell. Okay, now I'll explain the working principle of solar cell. So this is the circuit, this is the PN junction, this is the resistance, so this is the circuit, and this is the IV characteristic of the solar cell. So it works on the principle of photovoltaic effect and bias is not applied. So when radiation of suitable frequency falls on the diode, the electron hole pairs are generated. The free electrons reaching the N side are collected by the front contact and holes reaching P side are collected by the back contact. Thus the P side becomes positive and N side becomes negative, giving rise to the photovoltage. When an external load is connected as shown in this figure, so what happens is a photocurrent I, that is current I, flows through the load resistance R. So this is the load resistance R. So the current will flow through the load resistance R. So the IV characteristics for this photocell is given by this thing. Okay. Next, the uses of this solar cell. So solar cells are used in satellites and space vehicles and also power supply to some calculators. I'll repeat again. The solar cells are used in satellites and space vehicles and also power supply to some calculators and other domestic purposes also. Used in charging storage, used as the charging storage in batteries, so etc. The important criteria for the selection of material for solar cell fabrication is, so the first one for this is band gap. So the band gap is around 1 to 1.8 electron volt. The second one is high optical absorption, which is around 10 to the power of 4 centimeter inverse. So the third one is electrical conductivity. Yes, electrical conductivity is high here. So the fourth one is availability of the raw materials. The raw materials for the preparation of the solar cell is very cheap. So it is very cost efficient. So sunlight is not always required for a solar cell. Any light with photon energies greater than the band gap can do the job here. So the solar cells are made with semiconductors like silicon, gallium arsenide, etc. The next topic is digital electronics and logic gates. So the first term in this is analog signal. The signal which has continuous time varying voltage or current is called as analog signal. I'll repeat again. The signal which has continuous time varying voltage or current is called as analog signal. For this, the example is voice signal. So you might have observed that our voice signal varies continuously. So here it has increased. So then again it decreases, again increases and again decreases. So like this it happens. So this is an example for analog signal. The next term here is digital signal. The signal which has discrete values of voltage or current with respect to time is called as digital signal. I'll repeat again. The signal which has discrete values of voltage or current with respect to time is called as digital signal. So the example for this digital signal is square wave or pulse wave form. So this is the example for square wave. So this figure shows the a pulse waveform or square wave which has only discrete values of voltage. So what happens here is it is convenient to use a binary numbers representing such signals. So a binary number only has two digits, 0 or 1. So here it is 0, this point is 0 and this level is 1 here. So in digital electronics we use only two levels of voltage as shown in this figure. Okay, so such signals are called as digital signals. In digital circuits only two values represented by 0 or 1 of the input and output voltages are permitted. The next topic is digital electronics, the branch of physics which deals about digital circuits and digital signals is called as digital electronics. I'll repeat again, the branch of physics which deals about digital circuits and digital signals is called as digital electronics. So there are two levels in digital circuits. They are 0 and 1, or off and on, or low and high. So there are only the two levels of digital circuits. So they are 0 and 1, or off and on, or low and high. So George Boole developed the algebra for the working of digital circuits called as Boolean algebra. It is based on the binary system. It uses two digits. They are 0 and 1. So the next one is logic gates. A logic gate is a digital circuit that follows certain logical relationship between the input and output voltages. I'll repeat again. A logic gate is a digital circuit that follows certain logical relationship between the input and output voltages. So there are three types of logic gates. So the first one is OR gate, the second one is AND gate, and the third one is NOT gate. So the logic gates are classified into three types. First one is OR gate, the second one is AND gate, and the third one is NOT gate. Logic gates are used in calculators, digital watches, computers, robots, industrial control systems, and in telecommunications, etc. The next topic is truth table. So it is a list of all the possible input logic level combinations with their respective output logic levels. I'll repeat again. It is a list of all the possible input logic level combinations with their respective output logic levels is called as truth table. So in that, the first one we have NOT gate. So I'll explain the first one, that is NOT gate. So NOT gate is also called as inverter. So why it is called as inverter, I'll explain to you now. So the logic gate which produces the output 1 if the input is 0 or vice versa. So if the input is 0, we'll get the output 1. If the input is 1, we'll get the output as 0. This is why it is called as inverter. Okay, so it produces an inverted version of the input to an output. So this is why it is called as an inverter. So this is the most basic gate. Okay, with one input and one output. So this is the symbol of NOT gate, and this is the truth table of the NOT gate, where you can easily see that when the input is 0, the output is 1. When the input is 1, the output is 0. So Boolean equation for NOT gate is y is equal to A bar. So it is read as y is equal to not A. So it is read as y is equal to not A, where A is input and y is output here. Okay. The next one is OR gate. So the logic gate in which the output is 1 when any one of the input or both of the inputs are 1 is called as OR gate. I'll repeat again. The logic gate in which the output is 1 when any one of the input or both of the inputs are 1s is called as OR gate. So this is the circuit symbol of the OR gate. So this is the truth table of OR gate, where you can see that 0, 0 is 0, but 0, 1 is 1, 1, 0 is 1, 1, 1 is 1, 1 is also 1 here. Sorry, 1, 1 is also 1 here. So this is the truth table. So as the definition itself says that 0, 1 is 1, 1, 0 is 1, 1, 1 is also 1, but 0, 0 is 0. So definition says that the logic gates in which the input is 1 when any one of the input or both of the inputs are 1s is called as OR gate. When both of the input 1 is 1, 1, 0 is also 1 and 0, 1 is also 1. But when 0, 0 gives only 0 itself, it is not 1. Okay. The Boolean equation for this OR gate is y is equal to a plus b. But it is read as y is equal to a or b. Y is equal to a or b. The next one is AND gate. So the logic gate in which output is 1 when all the inputs are 1. I'll repeat again. The logic gate in which the output is 1 when all the input is 1 is called as AND gate. So this is the circuit symbol of the AND gate and this is the truth table of the AND gate. So as the definition it says when 1, 1 is 1 but 1, 0 will give 0, 0, 1 will give you 0 and 0, 0 will also give you 0. So the Boolean equation for this AND gate is y is equal to a dot b. It is read as y is equal to a and b. It is read as y is equal to a and b. The next one is NAND gate. The NAND gate is an AND gate followed by a NOT gate. If inputs a and b are both 1, the output is 0. I'll repeat again. The NAND gate is a AND gate followed by a NOT gate. If inputs a and b are both 1, the output is 0. The circuit symbol for this NAND gate is this one and the truth table for this NAND gate is here. So here 0, 0 gives rise to 1, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0 here. So it clearly shows that it is the exact opposite of the AND gate. So here the Boolean equation for this NAND gate is y is equal to a dot b bar, which is read as y is equal to not a and b. So remember that y is equal to not a and b. Next one is NOR gate. So NOR gate is a OR gate followed by a NOT gate. I'll repeat again. NOR gate is a OR gate followed by a NOT gate. Its output is 1 when both inputs A and B are 0. And when any one of the input is 1, then output is 0. So it has 2 or more inputs and 1 output. So this is the circuit symbol of the NOT gate, and this is NOR gate. This is the circuit symbol of the NOR gate, and this is the truth table of the NOR gate. So here 0, 0 will give 1, but 0, 1 will give you 0, 1, 0 is also 0, and 1, 1 is also 0 here. So only 0, 0 is giving 1 here. Apart from that, 0, 1 is 0, 1, 0 is also 0 and 1, 1 is also 0. So the Boolean equation for this NOR gate is y is equal to a plus b bar, which is read as y is equal to not a or b. Y is equal to not a or b. The next topic is integrated circuits, which is called as IC. So the fabrication of an entire circuit consisting of many passive components like R and C, which is resistance and a capacitor, and active devices like diodes and transistors on a single block or chip of a semiconductor using photographic techniques is called as integrated circuits. I'll repeat again. The fabrication of an entire circuit consisting of many passive components like resistors and capacitors and active devices like diodes and transistors on a single block or chip of a semiconductor using photographic techniques is called as integrated circuits. The most widely used technique is the monolithic IC. The word monolithic is a combination of two Greek words. Monos means single and lithos means stone. So this in effect means that the entire circuit is formed in a single silicon crystal or a chip. So this chip dimension, the chip dimension is very small and it is around 1 millimeter into 1 millimeter into 1 millimeter, or it could be even smaller. So the IC can be grouped into two categories. So the first one is linear or analog ICs, and the second one is digital ICs. So I'll explain the first one here, that is linear or analog ICs. The linear IC process analog signals, that is, it varies linearly and with the input. So as the name itself says, which is analog IC, which says that the linear IC processes the analog signals, that is, it varies linearly with the input. So the most commonly used linear IC is op-amp, which is called as operational amplifier. So the next one is the digital ICs. The digital IC process the digital signal that has only two values. They contain circuits such as logic gates. Next topic is classification of integrations on the basis of number of circuit components or logic gates. So the first one is small scale integration, which is also called as SSI. So here it is small scale integration is lesser than or equal to 10 logic gates per chip. So the next one is medium scale integration, which is called as MSI, that is lesser than or equal to 100 logic gates per chip. The next one is large scale integration, which is called as LSI, which is lesser than or equal to 1000 gates per chip. The last one is very large scale integration, which is called as VLSI, which is greater than 1000 gates per chip. So this is the end of this chapter, Semiconductor Electronics.